So hello, everybody. I'm Mike Oltman. I'm the Chief Technology Officer at AppRevita. I'm going to kind of walk through a story that we recently went through, a need to go from where we started at a nice, steady, moderate place and suddenly had to grow at a very large volume due to large customer growth. And so we're going to kind of walk through the story of the challenges and the way that we approached it, and really also talk about why MongoDB Atlas was a core piece of that story and how we used it to get to where we wanted to go. I'm going to start by giving you some context, by introducing AppRevita a little bit, just a couple of pieces there so that you understand the challenge that we're coming against in the healthcare space specifically, and some of the things that we do. So AppRevita is looking at being a platform as a service for the health industry. Health industry has a lot of different use cases, a lot of things, but one of the things that they've been realizing over the last number of years is they need to do a lot more with a lot more of their data. They really need to harness the data that has now come out of moving to electronic record systems. They have a lot of electronic systems, a lot of data, but they're not really getting the value of it. And you think about the ability to help the quality of care, the ability to help the healthcare industry do things smarter, more efficiently, inform the doctor and the nurses and the clinicians information that they need to make faster decisions. Sorry. So this is what we're trying to do as an organization. When you think about that challenge, you have patient records. We're not talking about aggregate data and doing huge charts where you're summing it up. You literally have to run analytics and algorithms, thousands of these, against individual patient records. Your patient record from the hospital, my patient record. Merging it across the doctor you went to, the surgeon who worked on you, and the triage nurse down the hall from there. So this is a challenge that we had to do. And so we believe that we had to build this open, secure, industry-scale collaboration. We had to build a system, and the industry is looking for a platform as a service. They build a lot of one-off tools. Here's 3 reports. Here's one process. Here's a tool that basically manages the calendar of a doctor, right? But what they're looking for, in order to get all of the algorithms, all of the data, and all of the processing that they need to do, they really need a platform as a service that is really founded on cloud technology, distributed technology, lots and lots of computations per minute, per hour, per day. And that's what we're trying to do. And the use cases really go across the whole industry. Clinical decision support is really key. It's basically the ability to say, they've got your lab data, they got your triage data. Is there anything about you that we should basically have the nurses or the doctors check into before something goes wrong? Why wait until the problem? It's really complicated with people, but it's really something that they're focused on. Quality measure reporting is really retrospective analysis. How well did the hospital do in the outcomes of their patients? How many patients needed to go back into the hospital and do readmission? By the way, a lot of these institutions are now being penalized by CMS and by other companies in the government and the insurance companies if they allow too many readmissions, if they don't solve these problems. And so they need to process all this data in order to both save lives and be more cost efficient, because it can cost them millions and potentially hundreds of millions of dollars to not do this correctly. So they need to cooperate across organizations, right? So it's not just one hospital, it's an entire network of hospitals. It's not just one doctor's office, it's the doctor's office, the hospital he works in, and the lab that the tests went to. All of this has to be worked through in an ecosystem, and this is the challenge that we had to face. An example of just e-pathways and decision support, some of the things that they have to do: gather the data, message it on mobile devices, manage the calendars, red, green on how well patients in the ER are doing, how to avoid sepsis. A lot of different things have to happen. This is the baseline of our challenge, because it's one thing to do it for a hospital. One hospital may have a couple hundred patients a day if they're a fairly large hospital. Those patients will have data coming in actually less frequent than you would imagine, but still pretty frequent, right? We're not talking about heart rate analysis. We're talking about the latest blood draw and the latest respiratory rates and some of those pieces. That's one hospital. What happens when you use a whole network of hospitals? What happens when the enterprise wants to know how well is the entire region of the Northwest doing dealing with sepsis or opioid abuse or any of those pieces? So I want to give one thing about our architecture, and I'll be very quick. It's a nice, simple diagram. We are a predominantly Python shop. We're hosted on Amazon Web Services. We use Django, Apache, different services using Python. We don't really have what I would call a logic tier as much as a compute tier and a grid tier. So all the data, whenever a patient records comes in, we've got to automatically calculate potentially hundreds of algorithms against that update to the patient record. And then we have our database layer, what we call our data grid. Our data grid is based on MongoDB. MongoDB is basically the elastic data grid that allows us to handle the growth of data and the constantly inputs of patient data. It's never going to shrink. Right? This is not something that shrinks. Your patient record just doesn't expire. There's no TTL on your patient record. And by the way, for those who are going to say, well, what happens when somebody passes? Your patient records stay around for up to 50 years in the government because they want to understand trends later. As new discoveries are made, they need to take your patient record to keep doing things. So there is no TTL right now on the data. So the data has to keep growing, and the processing space has to keep going. So what happens when we're supporting many individual institutions, and the bucket's just a little full? Hundreds of patients a day, hundreds of events per day, a limited historical backfill. We only really need 1 or 2 years of data because we're really talking about an ER situation or doctor's offices that you don't, you're just trying to do risk analysis. Millions of calculations per day on that data. What happens when you suddenly start doing enterprise health networks that have 250 hospitals, 3,000 hospitals across the US? You have a different data problem. You have a different scalability problem. And so as an institution, we asked ourselves, what should we do? How do we go from where we were? Because now that we're getting growth, now that we're signing customers and having hundreds of hospitals join our customer base, where do we go from here? What happens when they want one set of reports for one hospital, but then they want to roll it across their entire region to an enterprise view? Ministries of institutions. What do we do about that? Well, we started with 200 gigabytes of data, a couple of shards, 3 shards, kind of a nice, straightforward, simple installation. 300 compute engines, so that different 300 CPUs running the calculations all the time. Data growth of hundreds of megabytes, per day, per week, not a lot. Our target was 20 terabytes. We thought we would need at least 9 plus shards, potentially 12, potentially 16. And growing. It's not going to shrink, as I said. We were going to need much larger instances. We were going to need instances with much larger disks on them. 10,000 compute engines a day, generating 10 gigabytes of data per day. And we had to support an initial load of 20 million patients worth of data. Right? So we had to go from a nice small bucket to a pretty full bucket. So we decided to call MongoDB. We said, look, we already have a partnership. You're our database vendor. We're working with you. We love your technology, but we are going to have to scale really fast. We have to do it in 3 months. Right? We have to scale all parts of our ecosystem. That whole architecture diagram has to get bigger. More compute engines, more database, more web server, more queues. All the things have to scale. But what we don't want to do is have a recipe where we build all the rest of the pieces and then we end up making the database a bottleneck, or we build the database well and we make the rest of our ecosystem a bottleneck. As we all know, these things are elastic. You have to keep stretching and keep running. This has to be a rinse and repeat cycle. Performance testing isn't just a, let's see where we're going, set a target and you're done. Performance testing is really about iterations. It's about setting goals and then iterating until you reach those goals. So we reached out to MongoDB. We decided an approach. We assembled a cross-organization team. We reached out to professional services. We said, look, we need a team of your experts to help us understand what we're doing to the database, to help us tune it, to help us know what's going on with it. We understand our application. We know where some of our problems are, but we're going to need you to help us with the problems that we might not be an expert on the MongoDB side. So we reached out to sales and we talked to professional services. They found us that team on site for 8+ weeks. We did an iterative methodology for testing. What's today's testing goal? What's this week's testing goal? Let's figure out what the environment needs to look like. Let's run that test data set. Let's spin it up, get the results, take those results, and tomorrow, do it again with a new configuration. Every single day, we wanted to run a new test cycle, adjusting to the previous day. It's the only way we're going to get it done in the timeline we had. Right? You have to just keep going as fast as you can. But you can't do it if it takes you 3 days to spin up a new server, if it takes your entire DevOps team to create an infrastructure. Right? You just can't do it. So you have to find a better solution. And since we were really born and built off of cloud technology, it was very clear that MongoDB Atlas was going to be one of our solutions. We built the project team. So at this point, I do want to introduce Anant Srivastava. He's basically our point of contact for the MongoDB professional services. We work with other great folks, some of who are in the room during the project. So Anand, if you can join, and we'll kind of go back and forth on some of the things that we did during this test cycle. But the key was enterprise architect and manager from Apervita. Our DevOps team, thankfully didn't have to do a lot, but still had to do somewhere. Our testing team, our development team, and then the MongoDB architect and application designer and the infrastructure designer. So we put together that cross-organizational team and said, all right, you guys, this is an 8-week project, maybe 10, if we're lucky, if we move fast enough. We got to kind of scale it 100 times. Is that okay? They said yes. So we invited them into our office. I talked about the daily stand-ups and testing goals, clear test definitions, dedicated isolated performance test environment. For all of you who are going to have to do the same thing, which it would be hard to imagine you don't have to do the same thing as our industries, all of our different industries are growing data day by day. You have to isolate it. You got to put that aside and let it just run by itself. Let that team run by itself. Constantly iterate. You don't want to affect your development cycle. You obviously don't want to do it in prod, although I've heard stories about that. So set aside that performance test environment. The great benefit for us is by doing that, we were able to say, we don't use Atlas today for our production environment, but we can use MongoDB Atlas for this performance test environment. We can prove its use, we can understand, we can day-to-day tune it, change it, tear it down, bring it up, change the configuration every single day. And that's why it was so key to the success of this project. I'll turn it over.
So to debug and identify critical paths, it was important for us to collect metrics at various levels of the stack, from top to the bottom, in each of our testing iterations. So for MongoDB, we use 2 ways. One is MongoDB Atlas. Like MongoDB Atlas provides you 20 different metrics in forms of nice graphs in the UI. Things such as connection churn, operation counters, WiredTiger cache utilization, WiredTiger queues, disk utilization, CPU utilization, etc. And then there is also a real-time tab in Atlas where you can actually see hot collections, collections that are heavily used, or top operations at any point in time. So we relied heavily on that. Other than that, we were also collecting MongoDB logs. And after each test iteration, we would actually thoroughly analyze the log files using a few tools. One of them is mTools. It is an open source software package that's available on GitHub. So we would use that tool to actually look at slow operations, connections, etc.
Sorry. That's okay. I think that, you know, what
was the reason to slow down your application? Was it MongoDB or your application?
It's a little bit of both, and it's actually covered in the following slides, so I think we'll get there.
We'll get into the
and if we don't
details,
answer the question with those slides, feel free to, we'll come back to that. But that's a very good question. One of the things that I always appreciate about the team that was working with us is they would always explain to us how to use the tools that they were using, which was great, but I didn't have the resources to figure that out at the time, right? I wanted to use those tools. I want my team to use it, but this is one of the reasons we reached out to the professional services team to begin with, is to say, like, I don't have the bandwidth. I don't have all the resources to do this thing. So being able to work with them and say, look, can you grab those logs and can you process and tell us what's going on? This was a daily conversation, and they found a lot of things that in our software could be improved, a lot of things that we might not have understood about the behavior of MongoDB. In the way that we were using it. And then they even found, one of the great things, they even found problems outside of that. They found some of the ways we were working with Amazon Web Services, we were doing it maybe not the best way. And so they found some of those pieces.
And
so
we're
we'll get
going
into
to
that.
cover some of that
Yeah,
on
we'll
later
cover
slides.
some of that.
Yeah.
The big thing is that bottom box, use technology that is flexible to scale, easy to rebuild and configure, and is fully instrumented. There's no way this project would have succeeded in the time if we didn't have Atlas, right? You know, Cloud Manager is great. We use Cloud Manager, but it's still not the same, right? For those who are on Google Cloud, Amazon Web Services, Azure, you understand that convenience of the database as a service or infrastructure as a service, infrastructure as code. It's really important to this process. And you know, this is obviously MongoDB world, and I can tell you all the experiences that we've had as a customer for many years. But part of it is also to understand why it's important. It's important because your goals are now to do a 3-month or a 7-month or a 1-year performance analysis. Your goal is to constantly iterate on your environment to make it better to handle your customers, right? So some of the benefits of Atlas and MongoDB professional services that we got out of it, we kind of covered a little bit that ease of scale and configuration. Being able to go into the menu and say, you know what, that M40 tier, we're pegging the CPU a little bit. Let's raise that up and see what happens. Maybe we need more shards because it's not really a matter of CPU bound, but storage bound, and we just need to store more data. But maybe it is also CPU bound, and we get better distribution, of course, in a sharded environment. Each night, if we weren't doing an overnight testing thing, we can pause the cluster. This is great for all of you CFOs, finance folks, or folks whose finance people yell at you all the time for how much your infrastructure costs. That's a really important feature when it's in a non-prod environment. We use this for our QA environment. We do this for our performance test environment. Are we doing weekend testing? No. Hit the pause button. Save a lot of money, right? It's a great feature. It's one of those things that I wish all of the cloud services just allowed you to pause for 24 hours without stopping the whole service. It was a wonderful part of it. VPC pairing, I know the talk before us talked about that. Very important. We're in our own AWS infrastructure. We have our own account. We're also a HIPAA compliant organization. All of our technology must use the HIPAA compliant pieces. So we have to be able to do VPC pairing. This is very important to us that we have our infrastructure, Atlas has its infrastructure, and we can talk in the most efficient way possible. And then the analysis of test runs and the recommendations and resolutions. We're going to get to some of this as Anant covers some of the iterations of what we did. But it was really one of those great things about working professional services is to be able to sit in a room and say, what are you seeing? Because this is what we're seeing. Did you notice that? Why is that call being so slow? Well, you forgot an index. Really? I thought we had everything indexed. Or you put the index on a non-sharded cluster, so you're not getting any benefit of your shards. You're hitting one collection way harder than the rest. Why is that? Maybe your application should cache that piece of data, right? That analysis of the iterative daily test runs and getting that feedback really was the reason why we ended up getting what we wanted out of the project.
All right, so let's look at a few key iterations and some of the important activities we performed and bottlenecks we faced during our test iterations. So for the first iteration, our goal was to stand up a performance environment which looked identical to the production environment so that we could run baseline tests. And so we stood up a 3-shard cluster based on M4.4x large instances, which have 16 CPUs and 64 gigs of RAM. And we attached a terabyte of EBS storage onto them, giving us roughly 3,000 IOPS. And then we executed our baseline tests. The first thing very early we found was one of the shards was used 3 times more than any other shard on the entire cluster. When we looked further, we identified that most of the unsharded collections that store operational data were actually sitting on that shard, generating all the traffic. So there were 2 options we evaluated. The first one was to actually just shard those collections. The second option was to move those collections to a replica set or a cluster of their own. We went with the second option because that helped us nicely segregate operational data from real customer data and set us up for a good multi-tenant environment. Next slide.
Yeah. I think I'll add one piece to that, which is we have 2 pieces of data, right? We've got what the platform uses, what kind of algorithm, what kind of information, a lot of metadata, healthcare. If you're familiar, there's a lot of metadata in healthcare. And then there's patient data. That is, the sacrosanct piece of data. You do not blink when talk about security, performance, and what we need to do with it. And they were all basically sitting on the same host. So as he said, finding the fact that we should split it was one of those aha moments. Sometimes you kind of hit yourself in the forehead and go, yeah, that's good, but that's why you need a second pair of eyes.
Yeah. So yes.
So we do this all the time. Our test environment basically is a mirror of our prod environment, and we basically do synthetic data. One of the things is knowing what a lot of the customer data looks like. You know that the different data types and the different dimensions of the data. It is complicated. What we try to do is find, say, 1,000 patients worth of unique data that fit pretty much a pattern that we see with our customers, and then just replicate that using actually our own tools that we do for all of our distribution millions of times. We,
Yeah.
yeah, right now we do.
And we also actually, in parallel, worked on generating, writing
That's right.
scripts, which were actually generating test data statistically,
Yeah.
following the bell curve and stuff like that.
Yeah, the nice thing about doing a performance test thing versus a quality test thing is the quality of the results is not what you're looking for, right? You're making sure that the data type is the same, so that way your algorithms run the same way within a % or two of performance. But then it's really just about quantity. So once you find that like 1,000 patients, there's in the industry there's a government agent or I'm not sure if it's government, but there's a centralized group called NCQA, and NCQA basically produces test data for the industry and standard data around that. And so we take that data as well and just basically figure out what it is, and then we just multiply it millions of times.
So we continued to optimize the code to make sure it is ready to scale. There are many things that we did, but I will just mention a few examples here. For example, the first one is using skip and limit for pagination. Now, the way skip and limit in MongoDB works is, it iterates through the entire data set to get to the point where you want it to. So let's say you are getting the first 1,000 records. Skip will start from 0 and go to 1,000. You want to get the next 1,000 records, it still starts from 0. If you're getting the 80,000 record, it still starts from 0. This works fine if you have little data, but with 20 terabytes, this was not going to work for us. You can't walk through really large data sets using skip and limit. So we instead implemented a range-based query mechanism using unique tokens, right? We also noticed that in the code, count was being used to count documents on a sharded cluster. Now, count has some issues with sharded cluster. I know we are working on fixing that, and in 4.0 actually we have already fixed count with predicates. But until then, we actually implemented aggregation framework to do the counts of documents.
I think it's worth mentioning that it's really because of a number of shards, right? And it says so in the documentation, but it's a little sneaky around that. So for everybody who has a sharded collection, I definitely recommend reusing it. It made a big difference.
Yeah, and especially when an active migration is ongoing or there are orphan records, then you may get something imprecise. We also made a bunch of index optimizations. We found indexes that were not used at all, but they were sitting there. We used the $index stats operator in aggregation and found those indexes. By the way, in Atlas, it just shows you the indexes that are unused. But this was more on the production side. And in-memory sorts, we were seeing a lot of queries that were using in-memory sorts. There were some queries that could be converted into covered queries. So we made index changes and to at least 6 indexes and optimized their performance by 10 or 20 times, actually.
And I think it's important that, the development team is really focused on doing these things. But even a development team with deadlines and all the things sometimes go, well, yeah, I thought we had that index covered. Or it was 6 releases ago that they built the index and then some other code changed and suddenly it's no longer covered. To be able to review this is now something we do more frequently, and this really brought it to light that we needed to do a repeated kind of index review after every release or two to make sure what we were doing, because not only is it not being used, it takes up space, it complicates things, it may even highlight that, oh, you changed the structure of the data a little bit, and you're not doing a covered query where all you have to do is update, drop and create a new index, and now you have a covered query. So index hygiene, even though the development team focuses on it, you kind of need something to help you on it. It's hard for everybody to always follow, and you kind of need that second set of eyes. And whether it's using Atlas or Cloud Manager and looking at that data tab, I know during the keynote today they showed that where it was showing the unused indexes. You then take that, you got to go back to your dev team, don't do what he did and just remove the index. But you take it to your dev team and say, hey, should we be using the index? Is the query written correctly? Where are we mismatched on this? And that was one of the things that Anant
and it's all about memory pressure by the indexes, right?
Yeah.
So let's move on to the next slide. Yes, so MongoDB provides you a good way to actually scale using sharding. One of the key components of sharding is Balancer, and the balancer actually moves data from a heavy shard to a light shard. So that means you have read I/O on the donor shard and write I/O on the recipient shard. And this may happen in parallel with your workload, with your real workload. So we wanted to explore scenarios in which we were actually pushing the envelope too much and looking into situations where we may not be able to afford to run with the balancer on. What we did is we actually came up with a smart shard key based mechanism where your shard key will hash to a certain shard and add a timestamp to it, and then combine that with zoning feature so that you could run with the balancer off and still be able to add new shards on it. I'll be happy to talk about it offline, by the way, if anyone has questions. But fortunately for us, we didn't have to go this route because MongoDB sharded cluster, for our use case, worked really well with the balancer on in all our tests. One other thing that we looked into was hash keys. Now, App-O-Vita's shard keys, some of them are hashed. And as you know, indexes are stored in a B-tree kind of format in MongoDB and a lot of other databases. Hash key, because of its very random nature, can actually, subsequent inserts can go to different portions of the B-tree. That means if you are an insert heavy workload, you will need a lot of that B-tree to be loaded into memory to continuously, seamlessly perform your inserts. So what we did is we analyzed the hash keys that were being used and looked at the corresponding workload and the amount of memory space those keys were taking. And again, fortunately, again for us, we didn't have to do any advanced modification to the way those shard keys were designed. But we were ready for it. We had done our analysis, and we were ready to deal with that as well.
There was one funny example, which was a hashed UID then being hash keyed again, or double hashing for no reason. So they're like, wait a second, we're looking at the raw database, and they're like, wait, your keys for this one collection is already a UID. It's already hashed. Why are you applying a hash key on top of that? Like, just get rid of that extra operation. Just things like that where a developer understood, yeah, I want to make sure uniqueness of this key, and then whoever went and added the shard key during the sharding was like, yeah, well, let's make that a hash key. That makes sense because we want random distribution. Well, it was already going to be random. There wasn't no need to do it. Again, a little bit of hygiene in there. To the question before let me just check actually, I'm going to let you do this.
Okay.
I want to address the question of the other things we found before the last slide.
Absolutely. So in ongoing iterations, our goal was to gradually increase the load and clear out any kinks on the way and make sure everything is scaling accordingly. So when we were doing that, we actually found issues at the top of the stack. Like there is a caching and a queuing layer, which is not built in MongoDB. But we had to actually look into that and scale it up first, and then shard the caching layer and add more nodes to the queuing layer. We also continued to refine the code and connection pool settings. As we were increasing load on the system, we were learning the usage pattern better, and we could actually tune the connection pool, things like pool size, min pool size, max time MS, etc. So we tuned all that on the way. On the Atlas side, we were hitting disk saturation because we started with 3,000 IOPS. That's what you get with 1 terabyte. And we were hitting those limits, and we were easily able to upgrade our storage through Atlas and add more IOPS whenever needed. Atlas instances also have a connection limitation. So like M40, I think at that point it was 4,000 connections. But because we have so many compute engines, we are scaling, so we suddenly go from 400 compute engines to 5,000 compute engines. They're going to make more connections. And so we had to actually keep a couple times upgrade the storage size just because of the connection number of connection limitations that we had on Atlas.
So just to kind of talk through what does a test cycle look like? What were we trying to prove? Well, let's say 1,000 hospitals each provide last month's worth of patients for a retroactive quality report. average at about maybe 5,000 patients per hospital, right? So now you're talking about 5 million patients worth of data being submitted, near the end of the month. That data comes in. We have to parse that data from their clinical format into a format that we can then use. So that has one grid, set of work that has to put the data into Mongo database in a distributed fashion. We're not going to do it serially, of course. Then after that data load is complete, it triggers off a number of algorithms. And those algorithms basically calculate whether or not that data had a reasonable quality first, right? So it's not even like a mathematical, is the patient okay? It's, is that data even worth evaluating? If the data is worth evaluating, what is the risk of the patient? If the risk of the patient is higher risk, do some additional calculations to try to understand what that risk is. And then at the end of the day, give them a dashboard that allows them to see who are the patients at the greatest risk, had the greatest readmission, had different outcomes happen, right? We're talking thousands to millions of calculations coming in at the time. Well, each CPU talking to the Mongo database, working on a particular patient is great, because each one is a different document in the MongoDB database world. And that means you have different threads and different connections distributed across your shard environment. That's all great until you then go from 1,500 compute engines to 10,000 compute engines. And suddenly the amount of writes going into the database and the amount of reads start to saturate it. So again, as he mentioned, you start to go, okay, we're going to need extra shards to distribute the load better. Better IOPS, because it's just the amount of IOPS that is really, not the amount of connections. Each one of those engines, when you get to 10,000 engines, has a connection pool. If you set it to the default connection pool, which we kind of did, it could create 10 connections. So now I've got 100,000 connections trying to talk to a 6-shard cluster. So max it to 1, because they're each single thread idempotent processes to calculate against a patient. Oh, well, that reduces the possible number of connections now. Things like this, you just iterate over and again, and having that extra set of eyes, again, helps you understand the different things that maybe it was a decision 4 years ago, that you suddenly go, wow, during the optimization phase. And everybody talks about premature optimization. There was nothing premature during this quarter. Everything had to be done. Every optimization we could think of, we had to run through. Our caching layer, not necessarily configured the right way. Actually, one of the MongoDB professional services pinpointed that for us. Like, this is just not working right. He kept talking to us about, like, it just doesn't seem to be stable. It doesn't seem to be at the right speed. We're not seeing enough load on the MongoDB database. There's no way you should have this minimum amount of load. We're like, okay, let's investigate. Oh, wow, we didn't configure that correctly. We didn't have the right number of shards for our caching layer. All of a sudden, the whole thing turns on its head. Now we have way too many connections and way too much things going on. Great, expand the MongoDB shards. To answer a couple more of the things that we found, let's see, some of the application layer was actually generating. We generate our own UIDs because of the de-identification process we try to do. We were doing that inefficiently. A lot of little things that you find during the test cycle. But one of the things we found is that we didn't need as many shards as we thought we would. As it turns out, once we got the ecosystem working, 10,000 engines, let's see, we were at
6,000?
Let's see, 6 shards, so it would have been 12 terabytes uncompressed, but of course we had a pretty good compression ratio, about 3-4 to 1, so we were able to get 24 terabytes, which was around what our goal was for this project. It was specifically 20, but give or take a few was always good. We were able to hit the 10,000 engines. We kind of started hoping we would hit 6, but we hit 10. 6 would have been acceptable, 10 was the goal, we hit it. We hit the amount of terabytes we wanted to use. I was happy that we had less shards, right? It gives us more room to grow. So, we were able to handle the load with the 6 shards according to that piece. We had a recipe for growth. We had looked at balancer options. We had looked at indexing things. There's a 30-page report I have that there are still plenty of things we could do a little bit better. And that's on our roadmap for the third quarter, is to do some of these things better. And we want to move to Atlas. And for those who don't know, Atlas now does HIPAA compliance. It's recently agreed to do that. So now we're able to move from our EC2 and cloud-managed instances into Atlas at some point. And the duration of the actual operation had to do that, 1,000 hospitals with 5,000 patients. Our SLA with our customers was 12 hours. We were able to hit it in actually about 3 hours. So this was the result of an 8 to 10 week project. It probably felt a little bit more to all the people involved, but it ended up being a success. We were very happy with it. We have to do this again. It isn't a one-time thing. We're going to reach out again when that next inflection point hits. when we go from having 1,500 hospitals to all the hospitals in the United States. That's our goal as a business, to help healthcare get better. But to do it, we're going to have to keep scaling. The data will keep growing. The number of algorithms will grow. Today, 5 or 6 algorithms for one institution. In a year from now, 200. That's our goal, right? It's a lot of data being churned. It's not just the data coming in, it's the data you produce. We will end up producing more data than they give us by factors of 10 to 100. Right? And we have to store all that and give that back to them in ways that they can analyze it. Because I can tell you that your patient record is not analyzable. You can get the entire hospital worth of patient records, and you won't know what to do with it at all. So you got to put it in a way and run these medical algorithms against it to get it to a point where doctors and clinicians and administrators can analyze. And that's the goal of AppRevita. And to accomplish that goal, we partnered with MongoDB. We used Atlas, and we were able to achieve our goals. I think there's only a couple minutes left for questions. I'm happy to stick around, but yeah, sorry. I'll stick around. I'll probably head outside in the hallway.
Do we have only a couple minutes or more?
We have a couple minutes.
Oh, okay.
So, anyone have anything that? Hold on, right here. So, go ahead.
How that traffic looks like? Is there like spiky or is that a continuous stream of data of certain volume or what you're dealing with?
It is. Oh, sure. Sorry. The question was, what is kind of the volume of the data? Is it more spiky? Is it continuous flow? Is it bulk and then quiet for a period? It's really more spiky. A lot of these institutions can't really give us a real-time feed, so they give us like periodic batch feeds during the day. Some of them will give us 1 feed a day because they're doing more retroactive analysis. But if they're doing clinical decision support, sometimes the best they can do is 15 minutes. A lot of times it's 5 minutes. So we'll get, the 50 patients worth of data that was modified in the last 5 minutes. They'll do kind of a database push to us, and then we'll absorb that and do the work. So I wouldn't say it's continuous, but when you get all the hospitals doing it at once, it's the spike goes up, it never comes all the way back down. It's kind of always sitting near the top, going up and down. Yeah. Sure.
You had a question? No.
I didn't get what was the querying and the optimizations that you had to do on Mongo, which is not in Mongo, on one of the previous slides.
Redis? Sorry.
Yeah, the caching and queuing layer optimization.
Yeah, so this is, in order to distribute the load of calculations, we basically distribute it. We use a queue mechanism to basically create all the tasks and create all the different actions that need to be taken. And that queue broker system was not holding up against the volume. So this is one of the things that was identified during the test cycles that was not related to MongoDB. And I think it's important to note that even though we partnered with MongoDB, when we talked to them in professional services, we kind of said, look, we need folks that know more than just MongoDB. And it wasn't a challenge for them to find. I mean, there's a lot of very talented people in the professional services organization. So the queuing layer and the caching layer was outside. I'm not going to call out those vendors. It wasn't always their fault. We had some of our own misconfigurations, but then there were some other limits that we ran into. So.
Yeah.
We actually talked, yeah.
So why you need so many computing agents? You use the MongoDB to get results, right? And it's secret.
So I'll give you one answer on why we need so many compute engines. The algorithms we run are not ones that we write. We actually have a custom online Python editor. Our customers write their own algos. They write all kinds of medical algorithms however they want. And so we had to have a way to compile and dynamically run their algorithms all the time. These are not SQL algorithms. They're not even algorithms that you can run a MongoDB query against. It's literally looking at all the data, correlations, value sets, coefficients, all this stuff goes into their algo. So the compute engine is literally compiling on the fly their algorithms and processing and linking it to their patient data. So it's not something where you can just give database access. It's really, it's hard to explain if you're not in the industry, but go look up metal.org and look at the thousands of algorithms they have. Those are the things that we have to run. So, yeah.
Cool. Thank you.